Okay, I'm going to hit it go live.
If it will cooperate today.
So it says I'm live on YouTube, and I can see our faces there. So
That's always good.
looks like that is broadcasting.
Perfect.
And what I'll do quickly there is just making sure we've got the right link there for folks. Let's just put that out onto LinkedIn right now.
All
And we
right.
can get started. So if you want to
Yeah,
start us off.
I will definitely start us off because I know it is 12 noon for me. So bright sunshine outside. I know it's 11 a.m. for Rich, and for our friends on in KSA, it is 7 p.m. So I understand it's at the end of your workday. Thank you so much for actually taking the time to join us today because, we know grease analysis is very important. Root cause failure analysis is even more important because this is where we actually get some information on how did it fail, why did it fail, and this is what helps us to prevent these failures in the future. And of course, Rich has been going through so many failures with these different types of grease analysis, and he is the expert on it. And I know he will be sharing a couple of case studies with us today. And just to let us know, I see it's now starting to record. Just to let us know how we're gonna do that processing in terms of why do we want to understand this? How are we going to go about performing an actual failure analysis for grease? Because a lot of times when we have failures in the grease realm, we're just like, oh my gosh, it failed. What do we do now? We don't get into find out the real reasons. And what happens is that we have more parts failing going forward, and that's not what we want. So Rich is here to give us some very good tips and to share some of his experiences with us working in the lab, going through all of these different types of analysis with a lot of different types of equipment because almost everything has grease in it. That's very real. So once it moves, it either has oil or it has grease in it. So Rich, I'm gonna pass it over to you so you
Great.
can, help us out and let us know all about what we need to do with these sort of failure analysis.
Sure thing. Thank you, Sonia. And really, we wanted to pivot to failure analysis here fairly early in our series, talking about the grease thief coming to KSA, because as you think about early adopters, when we have a new option for technology, early adopters are probably going to be thinking about how can I solve a problem? How can I address something that's already an issue in my facility, my plant? And so it's natural that root cause failure analysis becomes a way to adopt grease analysis techniques and learn more about these failures. Because as you're indicating, it's not just about one particular bearing or gear or whatever. It's often the opportunity to learn about systemic issues, about using the right or the wrong grease, about the right or wrong amount, about contaminants and things like this. So let's talk a little bit about what sets us up for success with the root cause failure analysis. And it's where, we want to have an investigation into the unexpected failure of an equipment component. And it's really important that evidence is carefully and thoroughly examined to determine that root cause of failure. Ultimately, with the data, we're going to be able to create a timeline that highlights the key events that lead up to this failure and gives us some recommendations for the future. So we look at, our routine inspections of equipment that are out there to collect data, process data collection. And we want, where possible, to have this information available as part of the root cause. Look at what kind of lubrication activities have been out there. Are there level checks? Has greasing been taking place? Is there any logging of this? And review our procedures to see if our process is setting us up for failure. And then another piece is information preservation. And so what I want to do is differentiate how we approach root cause failure analysis of greased machinery differently than maybe others might. And part of this is in this information preservation. So a lot of times when someone is concerned about a bearing failure, they'll say, save the bearings and send them off maybe to the bearing supplier and have them look at it, right? Because they're the experts. They make the bearings and they're providing them. And usually that step involves taking the bearing and the parts to a parts washer so that solvent is run over them and they're cleaned up. And then these clean bearings are sent to someone for inspection. But what we're doing is washing away some of that evidence, right? We wouldn't approach a crime scene where someone has been injured or shot and immediately start hosing down the area to clean it up, right? Because you'd be washing away evidence. And so we treat it the same way. We want to preserve that evidence. We want to limit access to the area. Someone who's trained and focused on this should have some direction authority. We want to document things. We want to preserve small or manageable parts. We want to take some as-found dimensional data and then photograph all the parts that are too large to save or to move, or all the conditions that have to be disturbed to perform the repair. So again, we want to get the plant back up and running, right? But we don't want to lose information in that process. It has to be preserved. So we save the parts. We don't want to bang them together. We don't want to pick at them or see if they stick together, because we're actually changing the surface conditions when we do that. So we secure and protect those parts from further damage. Don't clean them. Don't put them in the parts cleaner. If there are
I think we lost Rich for a bit there. I think we lost Rich for a little bit there, but just going back on what he was saying is very important when you have these parts come in, that you do not clean them. A lot of times we're so focused on just getting the plant up and running. We lost you for a bit there, Rich.
Yeah, so I to try to help with a better connection, I hardwired me into
Uh,
the network. Maybe that's the problem. So I've disconnected and I'm just going wireless at this point,
that's
and
okay.
yeah,
That's
hoping for
all
the
right.
best here.
I was just reinforcing the fact that a lot of times we're so focused on getting the plants back up and running and making sure things operate, that we clean the parts up and we forget that we need to do an investigation on it, and we're really destroying all of the evidence that we need. So I hear you 100% with what you've been talking about so far.
Yeah, early in my career, I did a lot of what I call dumpster diving, where, by the time I was made aware that we had an investigation to do, parts were already thrown away, because the focus is on getting the plan up and running.
Up and running, yeah.
So I'm going to talk a little bit about the importance of saving that information and not cleaning. So if we have fluids, we want to drain them into a clean sample container, or seal into the part, or extract the grease that might be there and submit that along with the bearing or the parts for analysis. And then there might be a component where we have to interview some folks, right? Who was involved? Who was involved in setting the machine up? Who might be doing inspections? We don't want to assign blame. We just want an honest search for the truth. And that's really important as we approach these things. We want to establish a positive policy for our root cause failure analysis and make sure that we're not affixing blame and reprimanding folks, but we're working as a team to find out what happened so that we can do a better job going forward. So the corrective action plans that we come up with are going to look to identify similar component failure modes. In other words, we had this one component that failed, but how do we then apply the knowledge that we learn to other parts of our facility, other parts of our company that are similar or have similar processes. We want some short and long-term plans and assign them out. And then, of course, we got to have a priority on restoring the system to operability. So you balance that immediate production concern with the importance of collecting the data that's necessary to understand why this failure happened. And then, of course, a lot of times once the machine's up and running, the attention turns and we don't follow through. So we need to follow through on these steps of having collected the data, analyzing the data, finding the issues, and then making changes in our facility. So how do we start out? If our component has failed, what do you do? The first thing is make sure that the scene is safe. Wherever this failure happened, make sure there's not any retained energy, compressed air, springs, pressure, what have you, that could be released by someone trying to inspect or remove parts. And then there is what we do is we created a kit, a root cause failure analysis kit. Now you could make your own kit, and I'll show you how our kit works for this, but it's something that helps walk someone through the process. And we don't always know who's going to be there collecting the materials. So in our kit, we include a QR code that can be scanned, and that inputs the failure inputs to the failure analysis team. It puts the equipment type. It lets you enter the operating history, the symptoms that you saw, the system parameters, the conditions were observed, and then an analyst gets assigned to that case. So they're going to follow you through when you submit the parts through the analysis that happens in the lab. And then all the evidence is collected, and there's instructions on how we secure that. So here's what the kit looks like. It's got some heavy duty, because a lot of times the damaged parts are sharp. They want to poke through thin plastic and so forth. So we got heavy duty, thick, sealable bags. We also have these sealed air Instapack foam. So you want that bearing not to bang around as it's being shipped and have additional damage taking place, but you want it to arrive at the lab or the area where it's going to be inspected in the same condition it was found. And that's what the foam packs will do. You break these foam packs, and they will form a foam secure environment around the parts so they don't get further damage. It has GreaseThief samplers in there. And of course, in this series, we've talked about how we use these sleeves to extract the grease and take the sample. There's oil sample bottles there because we may have some oil that would run out of the machine or still be in the reservoir. And then there's some instructions in there to help use all this. It's durable, it's a waterproof, and it just seals up tight and you're ready to go. So that or something like it. What we don't want to do is we grab the bearings and we just throw them into a box. Or I've even had stuff that gets shipped with packing peanuts. And the material of the packing gets into the parts, and you can't really discern what was there and what got added. So we make sure that it's safe at the site. We get the power off. We access the equipment. Make sure that nothing has built up for pressure. And then, of course, we want to clean up any hazardous spills and alert people walking through that site. And that information preservation is essential to piece together the cause of the failure. Again, do not clean the parts. That is valuable data of the analysis that will be washed away if an attempt is made to clean them right on. And then, of course, we're going to drain all that and submit that as well. We're going to package it and securely label it, put all the components in the heavy-duty bags, and then we inflate this expanding foam. And it's all secured for the trip back to the investigating place, where you can see quickly insert all the parts. The expanding foam is on top and on the bottom, and then it gets shipped back, right? So what I want to do now is add some case studies. How do we actually go about looking at both, in this case, the grease itself, as well as the parts that were submitted? And I'm going to share a few case studies. I do have one here that's a tunnel boring machine. And this is something that we see in some areas where subways or other roadways or place, or even for utilities, piping and so forth, that these tunnel boring machines can go beneath the surface of the soil and then run vertically for great distance. It's a complicated machine that can be quite large. And I've got one history here where we worked to do grease analysis on the world's largest, at the time, tunnel boring machine. It broke down and some years ago, and $80 million US was spent on clearing the debris and inspecting for a root cause. So down underground, under the city at the time, very expensive to find out why this failed. No cause was found. It was suggested that they must have run into some old piping or some old buried material that broke the head. But no smoking gun, as we say, nothing definitive. But they're under schedule pressure, so they started this tunnel boring machine up again, and it immediately started to overheat. And at that point, we were brought into the process, and a program of grease sampling and analysis was initiated to find the source of the bearing failures. Now, in this design, there were 4 different areas that were grease lubricated, including some bearings, some support gears, the cutter heads, and some of the linkages and so forth. And so each of these sections were separated by a sealing mechanism. When we sampled each of these using a GreaseThief tool that was developed for this purpose, each separate bearing section was independently sampled, and the grease from some sections were found in adjacent areas, showing that the grease seals had actually failed, allowing the grease mixing. When we saw the grease mixing, we found that there was incompatibility between these greases, and therefore, when the grease mixed, there was not adequate protection for the bearing. This was leading to that bearing damage. Finally, once it was understood what the root cause was, in this case, failed seals between the bearing sections, as evidenced by analysis of the grease and the evidence that different greases in different sections were being mixed together, they were able to correct that, truly find the root cause, and then immediately finish the tunnel. So this was one that was delayed for almost 2 years as they worked to try to understand and repair and have multiple false starts. But it was finally finished just a few months after grease analysis found the root cause of the problem, and it saved probably close to $1 billion US in avoided cost of another restart without correcting the root cause. And so obviously a big benefit to grease analysis in that case. And it wasn't one where it was originally recognized that grease analysis held the answers. There was engineers just looking at the design and coming up with their own ideas of what they thought must have happened. Only after testing was it clear what the true root cause was. I've got another example here from a ball mill that's used to crush stone, and these happen to be in coal service, but we've done this type of analysis in multiple different crushing, different ores, and so on. And so the samples, we had 2 side-by-side coal crushers in identical service. They had the same time in service. And as we looked at the grease, what we saw here was that there was a very different response in terms of the antioxidants. So this is the ruler test. And ruler test is one of the tests that you can apply to grease samples and really see what's happening over time as the grease is exposed to the stresses that application has. And that would be temperature, it'd be the working of it, it would be contaminants getting in, and the duration that it's there. Over time, these antioxidants break down. But here we would expect these 2 different bearings to have the same response because it's the same surface, same conditions, same period of time. But you can see the lower graph here, the red line, which is the graph of the antioxidants present in the grease sample. the lower graph is much, much less than the upper graph. So we've consumed a lot of these antioxidants. Now, going back with this information, we were able to do a thermal analysis, and we found that the lower ball mill was overheating. It was running 35 degrees Celsius higher in temperature than the upper one because of some alignment issues. And as a result, that excessive heat was breaking down the grease. So in this case, the grease was not the root cause, but the grease had the information that allowed us to point towards one particular cold crusher and finding that a combination of excessive heat and misalignment in its setup were sending this to early failure. And so it's another kind of example. I want to share a third example here, a kind of a detailed one. And so I'm going to swap out from this view here to a root cause failure investigation report, a full report that we have here. And hopefully you can see enough on the screen here to see the detail. And this one actually came from the Middle East. We were working with a company that did vibration analysis at a gas-fired power plant in the Middle East. I'm not going to say exactly which one, just to protect our customers and that sort of thing. But you can imagine the environment that this is working in, and they were getting high vibration levels and shutdown, and they wanted to understand why that was happening. And vibration analysis is a very effective tool, but often you're just given the symptoms of what's happening, right? Something has caused this bearing or these bearings to operate differently than intended. And eventually the wear builds up to a level where the vibration is excessive, but it doesn't necessarily take you back to pinpoint. You might be able to say, well, it's the inner race or it's the outer race or it's the balls. And this frequency tells us it's the ball coming over a fault on the bearing. And that's all very helpful to understand the nature of it and maybe how much life is left or how rapidly it might progress to failure. But it doesn't necessarily tell you what caused that initial problem to start that led to the high vibration condition. And so this is how we would go about doing the root cause failure analysis. And the background here again is like I'm sharing. It's the vibration analysis had abnormal indications of abnormal damage. Both bearings were then removed and submitted. Fortunately, they were not cleaned, so we had the grease available that we were able to sample. And so the process is it comes back to the laboratory, the grease is extracted. Now, sometimes you can just take one sample and that sample pretty much tells the whole story. But sometimes in root cause failure analysis, we're going to take multiple samples, especially if there's a visual indication that not all the grease quite looks the same. Or perhaps we can sample some grease that appears to be on its way in, like the new grease being added, versus some grease that's been there a while, and then the grease that's right there under the rollers at that point in time. So we can kind of take multiple samples to put together more of a story about what's happening there. And we're also looking for any kind of debris. Sometimes there's loose parts or other debris that we're surprised by. So the methodology for the grease analysis is to look for the metals that are there, to do Fourier transform infrared or FTIR, to look at the antioxidants. We saw that in the previous example. Do microscopic inspection of the particulate that we separate by patch or ferrography, and then rheological analysis to look at the condition of the grease relative to what new grease looks like. And so you can see that's what we did here. And then we also look for things like the client sent some photographs, some engineering drawings. We looked at the vibration data, and we're putting this all together to better understand what's happening. So we know what the baseline grease is, and we use that in all of our comparisons. And so I'll just continue to look along here and kind of maybe blow this up so you can see it. And here we have the first is the FTIR. And the FTIR is really thought of as a fingerprint. That's what this top image is here, the FTIR. And we've overlaid the sample, which is in blue, on top of the green, which is the baseline. And so as a laboratory, we may have multiple baselines in our libraries, but we always look for the company or the individual doing the root cause failure analysis to submit a new sample of the grease that they are using for a few reasons. Number one is you can see what is the condition of that new grease, but also formulations change. And as you go around the world, different areas will brand the same product with slightly different formulations. So we always want to do this comparison to the source that's being used for that particular plant in that location. And what you can see here is these align pretty closely. Some of the peaks have a little bit different difference in amplitude, but this is a pretty good match. So we're not seeing evidence of a completely different grease being mixed in here. We're not seeing organic solvents and fuels and other types of things, sealants that can sometimes get mixed into the grease. We're not seeing that either. So this kind of affirms for us that it's the right grease. And part of root cause analysis is making sure that you're eliminating failure modes, right? So to confirm that something is as it should be is actually a good data point. We don't further pursue the idea that this was a mixture of greases. You can see here, this is the ruler test again, the green being the baseline of that grease and what we expect. And there's two peaks shown here. And then in the sample that was submitted or extracted from the bearing, you can see those peaks are present. It corresponds to being the right grease, but they're pretty depleted. Now, if this was a turbine oil, this would be an area of significant concern because there's very little antioxidant remaining there. But remember how we treat greases, right? We grease a component and then we come back and we periodically replenish it. And so in this case, this grease is kind of at the end of its life cycle. What we would do is go back and find out at the time that the sample was taken, was this the time that they would normally be replenishing? And if it is, this would be acceptable because we've had the grease in there for a while. We're getting ready to put new grease in. It's consumed the antioxidants that protect it and shield it from oxidation, and we're putting new fresh grease and pushing it out of the way. So as long as we have a good and effective program of replenishing the grease, this would not be alarming. If someone came back and said, oh no, this sample was taken at a time when we would have been 4 months away from adding grease to it per our current program, then you would raise the concern and say, this would indicate that you're not greasing it often enough. So that's where it's really important to get that reference point from the operating organization to understand, what the practices are as we assess things. So here is some of the analysis. We talk about the fact that there's excessive wear here. But we say the excessive wear can often be a symptom rather than the cause itself. We found a very high iron concentration in the grease sample. So we had the early stages of a bearing failure. And there was some trace amounts of silicon and aluminum. And so silicon and aluminum, really important. These are key components in sand. And remember, this was a location in the Middle East. And so this is obviously something that we're constantly fighting against, trying to keep our grease supplies clean, trying to keep the machines protected from that environment. And these fans did sit outside in this particular design. These were located external to any enclosures or buildings. And so these were really subjected to the possibility of contamination. And silicon and aluminum really are two of the key elements that we would find in the sand. Now, if you're not sure in your working environment what elements are typical in the contaminants that can get in, I'm in the US, I'm in Pennsylvania, we have certain type of soil. It's going to be different makeup than say sands in around Riyadh. So what we would do is we would take a small sample of that, put it in a bottle and send it to the lab and say, here is some of our dirt. Here is some of our sand. Here's some of the contaminants that we find in our area. This is of particular importance if it's in a processing facility. Say it's some sort of mining activity or maybe cement facility. And you can actually look and get the ratios. The quantities don't matter, right? But the ratios, what are the elements that show up and what are the ratios between silicon and iron and aluminum and other contaminants that we can look for in the grease that show up when these contaminants get here. So this really was an indication of particulate contamination from the environment or possibly getting into the grease in storage, okay? And then you see here that there was also barium, boron, and calcium, which we, think of as some additives and some oils, but it could be also from foreign particulate and contaminants. So knowing what's there helps us understand where these things can come from. We saw that the consistency of the grease was elevated. It was thicker, or the grease was hardening a bit. We thought that could be a mixture of greases or a similar grease product with a slight formulation difference, or just the particulates making their way in. But you can see here's a severe cutting wear particle, what we might call a two-body cutting wear particle, or in this case, a three-body cutting wear particle that can be caused by an abrasive particulate or possibly some abnormal contact of the surfaces. And so as we continue on to look at this report, you can see we, under the microscope, and this is analytical ferrography, we have these lines of magnetic force that ferrography produces for us. We're actually finding these abrasive contaminants. Now, it wasn't in high concentration, but it could have been present at startup and maybe flushed away by relubrication. So if we had dirt that got into this at the beginning, or dirt was in the original packed grease that was in there, and then we came along with clean grease and we flushed it away, we wouldn't see a lot of the contaminants still there, but we might see the evidence of the damage that the contamination causes. And as we looked at the bearings themselves, that's part of what we ended up seeing. So here you can see, as we cut away part of the bearing, now we're taking the grease analysis results and we're combining that to the visual inspection of the bearing and its surfaces. And I don't know if you can see this, but right at that red arrow, there is a wear track, a line that cuts right down the middle of that bearing. And that's not normal. When you have a bearing that's properly designed and properly operating, that ball will rotate in random directions. So all the surfaces of the bearing kind of get equal exposure to the load that it's subjected to. But when you see a wear track on a ball bearing like this, that means it's been constrained. That means it's been prevented from rolling in that random normal pattern. And two things can do that. One is debris that can get jammed into the retainer ring and cause it to lock up. But when you see it circumferentially around the whole diameter like this, it means that it can continue to roll. This is usually due to misalignment or severe axial loading that forces that ball and forces the cage to pin that in one orientation and spin over and over again on a single wear track. So that's evidence right there that we've got something going on in that regards. And here at the lower one, you can actually see what looks like in this red box, the letter X. So it's like there was a wear track and then it was shut down. So that was released and then it started up again. And again, it was pushed into this constrained condition that made a new wear track that intersected with the original one. So it's very telling when you see these marks. So we've got another data point. We saw that there was a hard abrasive particulate in the grease. We saw some evidence of cutting wear in the grease. Now we're seeing some evidence of some abnormal loading. Let's see what else we find. Now we're looking at the outside surface of the bearings. And you might encounter this quite a bit. And this is a almost rusty or corrosive looking condition. And sometimes folks will see that and say, oh, there must have been foreign material, some kind of corrosive coolant, some other material that got on there and just basically rusted it away, or water or what have you. That's not what this is. This is fretting wear, and it's found here on the outer race of this bearing. And what that means is there is not a tight fit of the bearing to the housing. And when that happens, when you get this clearance in there because of improper fit, you get these surfaces smacking together, and that repeating action in an unlubricated contact. Because remember, the grease is going to be on the other side of this in the raceways themselves, not on the outside of the housing. So it's not on the outside of the bearing race inside the housing. So it is an unlubricated surface that will cause oxidation. And that oxidation is described as fretting wear. So I've got another thing. So I'm kind of counting up the list of indications, right? I'm not necessarily looking for one thing. And this is a mistake that many people make with root cause failure analysis. Did you find the smoking gun? Well, there may be multiple smoking guns. And if we find one thing and we say confidently, oh, it's this caused the failure, you may not be wrong. It may have been a contributor, but it may have been one of 2 or 3 or 4 different factors that diminish the life of that bearing. And if we only fix one, we're not preventing the next failure. We're just kicking the can down the road. We're just extending it out because it's going to come by one of the other failure modes. So here's a nice close-up, and now you're seeing right onto the ball surface, and you can see these scratches along the surface, and they should not be there. A ball bearing or a roller bearing is going to have a mirror-like finish. It's going to be a very fine finish with a very low coefficient of friction. That's how they're designed. Not only just because of the friction considerations, but you need that smoothness of finish to maintain that 1 micron or less lubricating film that you get in bearings like this. So these scratches are actually a pretty significant finding because they're going to disrupt lubrication and they're going to cause problems going forward. So this is where we're matching up to what was there in the grease analysis, the hard abrasive contaminant particles that we saw, the cutting, curly-Q cutting wear that we saw. It came from this surface and these surfaces. You also see evidence of the same thing on the matching raceway, where we have what's called particle denting. So as the roller is going over these particles, it's pushing them into the metal. The high forces and the high loads actually push them into the metal and make a dent in the metal, which starts a fatigue process. And as that fatigue continues, you get spalling, fatigue cracking, and finally damage and failure to that bearing. So we've got some evidence there. And then we kind of switched over to the other bearing, and you'll see us kind of repeating. Now we're at the drive end, and you've got same analysis here for FTIR. The bearing, the greases look similar. You have some oxidation of the grease, so you've lost your antioxidants again. Looks pretty similar. And then you've got some gouging wear here in the other bearing. The rolling element is sliding over a dent in the race and cutting out pieces of steel of the surface of both the race and the ball, and it's oxidized. So it's a very damaging a type of particle that's being formed there. And you've got some red oxides that are coming from that false Bernelling that we showed. Black oxides showing up as well. And this is this false Bernelling of the races. The bearing sits and vibrates without any rotation on the shaft. And we're not only seeing this on the back side of the bearing, we're seeing this inside the bearing as well, getting into the grease. So you've got similar things happening on these bearings, multiple damage conditions. And then the other thing you've got is here you can see the false Bernelling inside the raceway. So you can see these little, inside the red boxes, you've got these little dents. And they are dents that is put into the bearing when it is stationary. Now, that can happen from handling the bearing poorly before it's ever installed. It can happen while it is being installed. It can happen if the bearings are dropped. In this case, it's happening when the fan is turned off. What's happening in this false Bernellian case. And sometimes it's hard to tell whether it's a dropped condition, which is we might call true Bernellian, or if it's like hammered on, the bearing's hammered on, it's true Bernellian. But false Bernellian, in these little marks that you see, there will be an oxidized layer. And that tells us that the bearing is sitting there and it's chattering. And this is, for this root cause failure analysis to be effective, this is where we really had to go and find out more about the operation of these fans. And what we found is that there are two fans side by side. One runs for a period of time, and then it is secured and shut down, and then the other fan is running as well. And so what happened here is that the design on this was not very good, so that when one fan was running, it was actually causing the other fan to run backwards. It was loading up that fan and actually thrusting it off to the side, causing that thrusting pattern that we saw on the bearings, and then they would kind of run backwards. So they were skewed, the tracks, the wear tracks were skewed significantly to one side, and that's that reverse load. So a lot of times these bearings are designed to only load in one direction or primarily load in one direction. And in this case, having a reverse flow loading up the bearing and running it backwards was a definite contributor. So remember, we've talked about a couple of things here, and you'll see here that in the summary, we've got causal factors and root causes. So one root cause is that the standby vibration, while the fan is not even running, is generating false Bernellian marks on the inner and outer race. Another one is that the axial loading is indicated because they're off center. And that's really a lack of rotation in standby condition that allows that to build up, and the backwards flow. And then finally, you've got abrasive debris causing scratches on the surface of the rolling elements and making these impact dents, which leads to shortened bearing life. And then also the loose fit that we saw in the fretting corrosion on the outside of the bearing. So what do we recommend then? You want to ensure that there's free rotation of the fans as they are installed, and rotation during their standby operation, either by the common plenum flow or through periodic rotation. So they weren't adjusted properly for the design of this, and that was confirmed by going back to the manufacturer's recommendations. We also want to check the installation for free coupling float to relieve any axial loading that we would see on the motor bearings, right? So even if the fan is being loaded up, we should have some movement within the coupling that would allow the motors to find their center and not be jacked up in one direction, which is the case that we saw here. We also want to maintain good housekeeping to keep abrasive contamination out of the bearing and lubrication supply, especially during periods of extended storage. And we found out in this case that this was a project that took a long time to get underway, and some of these fans have been shipped to the site and were sitting by for over a year before they were actually installed. And so there was some question about how clean, how much contaminant might have worked its way into that while it was sitting waiting to be installed. And then, of course, we want to verify proper housing and shaft fits for bearings when they are being installed, and this could be a procedure that we add here. So again, if we really want to be effective at root cause failure analysis, we have to take findings like these and change our process, not just on these fans, right, but all the other similar equipment on site. And this is going to be something to be thinking about when we're operating in a harsh environment where there's a lot of abrasive contaminants, like we'll find in the kingdom and other areas in the Middle East. What does our grease supply look like? Are we protecting it? Are we keeping these abrasive contaminants out? And are we policing or inspecting our grease supply, doing particle counting of our grease supply to make sure that our practices produce clean grease being put into our machines to lubricate and to flush out contaminants that are inevitably trying to find their way in. So Sonia, that's what I wanted to cover today. I talked about some basics of the approach of root cause failure analysis, gave a few case studies, one from the Middle East itself that maybe could hit home with some folks, but also just to get folks start to think about how grease analysis can be applied. And I know that Hamza is with us today, and we had the chance to work with Hamza with a root cause failure analysis that he was working on, and I think that's part of what inspired him to ask us to focus on that. And he may have some thoughts on what he was able to learn. But again, when you've got critical grease lubricated components and you're not getting the reliability, the life that you're looking for, using this type of approach of combining grease analysis with the retention of parts and their inspection might put together that whole picture that lets us change our practices and improve reliability.
Definitely. And I just want to echo some of the sentiments that we've had coming in from the audience. A lot of people are asking if they can get a copy of this actual report, because the report was done really well. It identified different areas that I think a lot of people may not have been familiar with. And what I realized, even in addition to having the actual oil grease analysis parts, there are some places where our operators can actually look at the bearings and say, oh, okay, this is what I'm seeing going on here. I'm seeing those wear tracks, so I know that I have an issue. And maybe even during their turnaround periods or when they're doing some sort of changeover and just inspecting their used bearings, this could give them some insight into what they need to look at going forward. Start getting your, and I know it's always about convincing management that you actually have a problem, to let them help you out with getting that grease analysis program going. So this may be a basis for some of the people in the audience to say to their management, okay, well, it looks as though we're having these sort of issues coming in with contamination, getting that wear on your bearings. This can cause us this in the future. Let's start bringing in grease analysis to help protect ourselves from any sort of unplanned failure, because nobody wants an unplanned failure. And just start get that conversation going, because I think a lot of times when we're trying to convince management about getting grease analysis into our programs, that is a difficult thing to do because we don't have any evidence. We don't have any baselines to show them. So I love that you brought in the physical evidence, the process of going through the root cause of it all. And I know Hamza is, telling us, great examples here, and we still need to increase our knowledge within the kingdom. And not just the kingdom, because I know we have people joining us from different regions as well. And just based on the Trinidad experience, we do have a lot of dust here too, and it's Sahara dust, which I'm struggling with. But there's also a lot of contamination going on throughout the entire world. So I like the fact that you brought up the issue of bringing some of the contaminants into the lab to test them, to understand what your environment actually looks like, because that is something that is often overlooked as well. So back to my roundabout question: can the audience get a copy of this report that you've produced here today? We can send it out to them via email once we can share it with them.
Yeah, so this is one of my generic examples where
Okay.
I've removed all reference to the companies involved and so forth, and the statute of limitations has run out. So so I can share this, and I think it's a helpful learning tool, and like you say, maybe something that helps someone convince management to dig a little deeper on some of these things. But and of course, some folks, I've seen it on the message boards. I'm active on a couple of WhatsApp message boards with some pretty good activity in the Middle East, and you can tell that some people are kind of asked or told that they have to do the root cause failure analysis themselves with very little resources. So they're taking pictures and throwing them online, and and getting people to weigh in on them, which is a good place to start. But what I would say is, if you are doing that, if you're short on resources, I would say take the grease sample and set it aside before you do the cleaning, because you may find that you want to come back to that and try to add that data point later. And so start just by doing the visual stuff, but retain the grease sample in a clean container, get it extracted out, then go clean it off, and then start to look at it. You may have someone kind of cutting them open for you or whatever. We need to do that sometimes. But some of the things that I shared here are helpful. And there are some books and some charts that you can get from bearing companies and things like that have some of the common patterns that you look for. I would just caution that, what you'll see won't always exactly match up to that. It won't be a direct match, but it can be helpful in sorting some of these things out. So that could be a starting point. But again, hopefully we build up over time and we get support and resources to take this where it really needs to be, because the value of doing these effectively multiplies so many more times than the cost to get it done. Because we find, just imagine that, in this case that, that you've got a failure. Okay, that was one bearing that failed. But then you find that the grease is full of contaminants. And then you work backwards and you check your grease supply and it's all contaminated. So now you've identified a failure mechanism that's reducing the life probably by 50% of your bearings all through your facility. Imagine the multiplied cost savings of being able to definitively know that that's what's going on, because you have the data from grease analysis to go out and fix it. And so that's what I want to encourage people to work towards.
Definitely. And I like the idea that you spoke about in terms of one of the corrective actions from this case study, where equipment was just stored incorrectly. Or like I've heard of people storing bearings and then they are moving the bearings from one part of the warehouse to another side of the site, and the ground is not entirely smooth. So the bearings undergo some sort of vibration and they are damaged before they get into the actual equipment. So, things just to look out for when you have these things going on. But definitely starting off with grease analysis is a great place just to start getting thinking in that direction. And I know Hamza is asking about, if we already have ultrasound re-greasing in place, how can the GreaseThief and comprehensive grease analysis bring additional value to us? So what else can the GreaseThief do, even though you already have grease analysis in place, besides, of course, this root cause analysis, because that is very interesting to me?
Sure. So ultrasound will tell us when we have an adequate separating lubricating film or not. And it will also tell us late in the stages of damage that we have impacting taking place. Those are the two things that it does for us. And it's a huge part of improving the baseline of the effectiveness of your greasing program. And I really strongly believe in that. But it doesn't answer all the questions. It doesn't answer, was there a different grease in there when you started adding these greases and now you've got mixtures in there? It doesn't answer the question about contaminants like we saw in this case, where there's contaminants there. You would not see that in ultrasound until all of that damage had taken place and you can't really recover from that. Grease analysis can tell you early on, do I have the right grease? Is it mixed with something else, or is it in its correct state? Is it oxidizing? Okay, is it overheating or breaking down? Does it have contaminants in it? And if there is wear, how much and what kind of wear? So these are all added onto the ultrasound piece, which is so helpful and a great place to start, but it takes us to that next level, which is going to get maximum life. The main things that the ultrasound does is it keeps us from over greasing and under greasing our bearings. And that could be a huge part of the impact to lack of life or damage or failure. But all these other contributions of contaminants, mixing, different failure modes of like overloading and everything else that you can think of are all found in the grease sample. So they become very, very complementary. And so in addition to root cause analysis, it is something that we can spot check, that we can take a few grease samples here and there and put that up against, even before and afterwards, right? Because just because someone invested in ultrasonic greasing doesn't mean we're going to do this for the rest of the plant's life. Someone's going to come along and say, well, why are we spending time doing that? Why don't we just, roll that back or go back and grease once a year or something? If you can use the grease analysis to show the condition before and after doing ultrasonic greasing, that will reinforce the value of what's being invested there and ensure that it's not something that gets questioned later and removed. So it can help in another number of ways.
Yeah, and I like that because both of them are complementary. You ideally having one is good, but having the both of them that increases your program, increases the value that you bring to the organization. Because a lot of times we get that question, what can we cut from the budget? And sometimes our condition monitoring is the one that suffers the most, but it's actually ones that bring the most value. So being able to document the amount of value that it brings to your organization, that is a stepping stone in itself. And as Rich rightly said, can prevent you from that question of why don't we cut this part off. So I think it's very important when you have these sort of failures that you stopped before it happened. It's very important to document them because that helps you so much in terms of bringing the value to your organization and showing the value that you can bring to your organization because that's important.
And sometimes we don't really know what our problems are, right? I've gone to facilities where people say, well, we don't have lubrication problems, we just have bearing failures.
Yeah.
Okay. Well, because they were all put into the bad bearing category because we're not looking close enough to understand what's causing those bearings to not have ultimate life or maximum life. And so if we're not looking, we're not seeing.
Yep.
And by doing the grease analysis, we can see what we're doing right, but where there's opportunities to improve and better understand where we can get the most out of our investment in our assets.
Correct. I know we're coming up on the hourly mark. I am going to ask if any of our audience members have any more questions to Rich. I know Ahmed, thank you so much for joining us. He is saying that in Saudi Arabia, he experienced that oil monitoring is more than grease analysis is more in place. I think I'm mixing that up a bit, but I think what he's trying to say is that a lot of people spend more time on oil analysis compared to grease analysis. And in not just in Saudi Arabia, I think almost in most parts of the world, because they do not fully understand the value that grease analysis can bring. And we talked about it in that first case study with the tunnel. Nobody wants to have an underground tunnel collapsing on them while they're doing their work and having that sort of failure involved. And it was as simple, I'm going to say as simple as getting the grease analysis part going and understand what's going on with your bearings on that particular piece of equipment. And there are lots and lots of different types of equipment that just need that grease analysis to help understand about that failure. And I know Ahmed is asking about if you could explain on slide 11 about false brenneling, the red oxide and the black oxide. So I'm going to give that over to you.
Yeah, it's a good question. And red oxides and black oxides can be caused by different things. They're both oxidation of the underlying steel in the bearing. When we see small, I'll describe them as small pebble-like red and black oxides together that are similar, that's usually an indication of the fretting wear that I talked about, or the false brenneling. False brenneling is an example of fretting wear. Black oxides can also be caused by lubricant starvation. which is another possibility. Those particles tend to be a little bit different. They tend to be a bit larger. They're black oxides, but they're a little bit larger. They often have some unoxidized metal attached to the particles. And so most of what I saw here was more of the pebble-like similarity between these red oxides and black oxides. There can also be different red oxides as well. There can be kind of flat platelets that are more due to corrosion, like water getting in and rusting and so forth. So there's different types of oxides, and really we need to look at them in their entirety as we separate them through analytical ferrography to understand the failure modes that make sense. And in this case, being able to take it back to what we observe on the surfaces of the bearing, right? So in this slide here, where we're actually looking down, and you can't see it at this level, but when we magnified these little dents, there was actually a reddish brown tint to these dents, which told us that it was false Brinelling and not true Brinelling or impacting due to being dropped or hammered into place. So this is where the root cause, combining the grease analysis with the observations, really takes us to another level to understand the modes involved.
Oh yeah, it's all about, and that's the other thing with doing root cause analysis, being able to talk to your operators on ground and find out what happened as well. That helps so much. I know Hamza is actually asking, so when can we expect to see the GreaseThief and comprehensive grease analysis available in the kingdom? So I'm gonna put that to you, Rich.
Soon. I hope soon. Yeah, we're looking for different partners that can help make this happen. The first step is getting the kits in people's hands so they can do some things. There are some things that folks can do on site with some screening tests. There's a mini lab that we offer for grease analysis that allows you to look at wear concentration and also look at the color changes in the grease and be able to use that to see if the grease samples should go on for further analysis. We've talked to some other partners about getting laboratory capabilities within the kingdom as well and other locations in the Middle East. And we're hoping that the continued interest that we're seeing will help drive that. So what I would encourage folks who are looking for that is to reach out, give us some examples that you have, and we'll look to find partners that can get you the resources and the information you need as we build the capacity to see this laboratory analysis being performed in country as well.
All right, and I think that's about it that we have for today. So I know Rich will be sending me this report afterwards, and I will get that out to everyone on our mailing list, as well as, look out for our next date in March when we're doing our next installation. Any ideas that you all want to have, topics that you all want covered, always feel free to email us or, message us and let us know what you're thinking about, because we want to make sure that we provide information that's valuable to you, that you are looking for. So we hope you all had a good time today and enjoy these case studies. I know you all will be reading up some more on Brinelling and everything else going forward. So thank you all so much for your time today. I'm passing it back to Rich, and then we'll close off.
Well, thank you for everybody that participated, that asked some great questions and continues to show interest in this area. We want to continue to support that. Thank you very much, Sanya, for setting this up. It's great to work with you on this. You always bring great insight and really bring people together in this environment. So thank you for doing that, and I look forward to the next time.
All right, so we'll be seeing you all soon. Bye.
All right, bye now.